with a land acknowledgement. This event is taking place in Toronto, which is situated on the traditional lands of the Huron-Wendat, the Seneca, and most recently the Mississaugas of Credit River. This territory was subject of the Dish with One Spoon, One Palm Belt Covenant, an agreement between the Iroquois Confederacy and the Confederacy of the Ojibwe and allied nations to peacefully share and care for the resources around the Great Lakes. Today, this meeting place is still home to many Indigenous peoples from across Turtle Island, and I'm grateful to have the opportunity to work on this land. Acknowledging the traditional territory on which we live and work is a small but important step that reminds us to learn more about the Indigenous peoples in these regions, to consider the history and ongoing colonialism on this land, and reflect on how each and every one of us can contribute to reconciliation. You can visit native-land and who's.land to learn about the land that you're on or other areas around and to see who it belongs to. So if this is your first time attending AstroTours, we generally run our tours on the first Thursday of most months. And today we'll be having a lecture by Chris and me. And then after, we'll be heading over to the physics building for telescope tours and different interactive demos, and also have lab tours in the astronomy building. And it'll be of our long-wave lab, which works on telescopes such as the South Pole Telescope in Time, which is the Canadian Hydrogen Intensity Mapping Experiment, located in Penticton, British Columbia. Great. So, this is just a reminder that we have a merch store if anybody's interested that has our regular, Scribe, and Earth Hour logos. Okay. Okay. Also, AstroTours is organized and run by graduate students in the Department of Astronomy and Astrophysics, and have volunteers who are undergrads in astronomy, physics, and other departments. And we really appreciate your feedback to try to make these events better for everyone. So after today's event, please go to bit.ly/astrotours. bit.ly/astrotours to give us your feedback. We can always keep improving. Great. So our next tour will be in January. It'll be a lecture by Henry Leung about exploring our Milky Way with deep learning. It's going to be on Thursday, January 12th at 8 p.m., but the location is still being determined. And you can check our social media and website for that information closer to the event. Okay, so, cool. So now, on to tonight's speaker. Tonight we have Chris Mead. He is a PhD candidate in the Department of Astronomy and Astrophysics at the University of Toronto. He hunts for the earliest signals heralding the birth of supernovae from just a few hours to days after their explosion in order to study their natal mechanisms. Chris received his honors Bachelor of Science specializing in astrophysics from the University of Toronto. We actually did undergrad together. Aside from his research, he often sets up his telescope on sidewalks around the city in order to show his enthusiasm for astronomy. He was featured in the Toronto Star in 2014 as one of the 5-person Canadian national team that won the International Olympiad for Astronomy and Astrophysics team competition in Romania. So I'm now going to pass it off to Chris to tell us about seeding the elements, measuring the universe, the supernova mystery at the heart of astrophysics.
Testing. Everyone can hear me? Great. So I'm going to talk about the Type Ia Supernova origin problem, as well as why it's such an enduring and important problem in astrophysics and how my research is advancing us towards its solution. And the talk is going to be divided into 3 parts: seeding the universe, seeding the elements, measuring the universe, and the Type Ia Supernova origin problem. So first, some background. I go by many names, including my given name at birth, its anglicization, and the English name that I go by nowadays, Chris. I moved to Toronto when I was 6 years old back in 2002 and have lived here ever since. Nowadays, I often set up the department campus around town on sidewalks, and I take pictures of planets. See, these are some of the images that I took. And sometimes I take my telescope to events and trips hosted by the University of Toronto Amateur Astronomer Society, which is a club that I actually started in 2014. But for my talk, the first part, we're going to have to go much farther back than that, about 13.8 billion years to the beginning of the universe, so I can tell you how everything we can see, touch, and feel came to be. And this is a story about how the building blocks of matter were formed. So the universe today is expanding, and this is something that we can measure. If you extrapolate it backwards, we find that the universe must have started at a very hot, dense point that has no size, infinite temperature, and infinite density. And that is a singularity. Matter back then looks a lot different than matter today. Like today, this is the kind of matter that we can see. There's chemistry, complex organisms, metals. There's planets, stars, the Milky Way, and other galaxies. But all of this that we can see has what's called a binding energy. You can think of this as the price tag of a piece of matter. And it's the price that you need to pay to reduce that matter to its elementary components. For instance, most normal matter reduces at around 1 electron volt. This means that at 1,000 degrees, that matter will be reduced to its elementary components. It will no longer be the solid that you see it is. And even these elementary components, they're not really elementary. Elements are made up of protons and neutrons. And if you go about 1,000,000 degrees higher, from 1,000 Kelvin to 1,000,000,000 Kelvin, you will break down the fundamental building blocks of matter into their constituent neutrons and protons. And even the neutrons and protons are not actually fundamental. If you go an order of magnitude up from that, 1,000 degrees, 1,000 times hotter, then you can break those up into what's called fundamental particles. And this is about as far as we know. These may not be for sale, for all we know, but it's also possible that if you go to even higher temperatures, these become indistinguishable from each other, and the laws of physics are no longer what we know them to be. So if we know that the universe started as a singularity with infinite temperature, then if we extrapolate backwards, at some point, every piece of matter, all the price tags are affordable. Like if you go to only 380,000 years after the Big Bang, at that point, the temperature of the whole universe, even space, hits 10,000 Kelvin, and then the universe becomes an opaque photon oven. It's just the whole universe is filled with photons, and every photon that you hit is at 10,000 degrees. So there's no way that any matter that we can see, that we know and can touch, will survive. So this is sold. If we go back even further, though, into the oven, eventually we get to a point at 1 second after the Big Bang, and then no elements survive. If you take any element, it encounters a stray ray of light, and it will break down into its constituent protons and neutrons. So at some point, the universe is just a proton and neutron soup. And if you go even farther than that, back to 1/10,000th of a second after the Big Bang, even the protons and neutrons will become reduced into elementary particles. And at some point, you'll even encounter a point where the laws of physics that we know may cease to apply. Like at a certain point, some theorists predict that these elementary particles will unify into one single physical force. So instead of having, say, electromagnetism, weak nuclear force, and strong nuclear force, there's only one physical force. But this is not experimentally verifiable, and mostly due to the kind of orders of magnitudes of energy involved. So we don't actually know what happens beyond that point. So then we know that the universe started from this soup of particles. How did the actual matter that we see emerge? The first elements actually formed in the first 3 minutes, when the universe cooled down to a point when an element can form and not get disintegrated by every photon it meets. So at that point, you can have a process called nuclear fusion, where you have smaller elements combining and they form heavier elements. So you hit protons together until eventually you get a helium atom, and then you can hit those together and try to get heavier and heavier atoms from them. And the reason why this is happening is because heavier elements, turns out, are actually more stable than lighter elements. Like this is a graph of the binding energy, the price tag, versus the number of nucleons that are inside of a nucleus. You can see that iron is actually at the peak, which means that iron has the highest price tag. It's the hardest element to disrupt. So every element actually eventually wants to become iron, because at lower atomic mass numbers, it's actually less stable. And this is actually what would happen. Like every element would just eventually become iron if we let this process go on forever, this nuclear fusion process. But the problem is this nuclear fusion requires energy. Like protons don't like to stick together. You have to smash them together in order to make this happen. And the universe is expanding. It's cooling. It's not waiting for anybody. So eventually the universe cooled to a point where nuclear fusion was no longer possible. And instead of getting all iron, we're left with still mainly hydrogen, about a quarter helium, and almost nothing else. And by almost nothing, I mean literally almost nothing else, 10 to the minus 12%. So that's 0.1201% of other elements that are heavier than helium. But today's elements are not quite like that. There's a little bit less helium and less hydrogen, and we have 2% other elements. You might think that's kind of weird because we have almost no hydrogen and no helium in this room, right? Otherwise, if it was all helium, I would be talking like Donald Duck. But, and if it was all hydrogen, it would be like, this would not be a survivable atmosphere for me, to say the least, right? What we have instead is, these are all elements that are mainly locked up inside of stars. Everything that our planet is made of is mainly what's in the latter 2%. And this 2% of elements is composed of what we see here. And we can actually see that in the current universe, these elements form what's called the iron peak. And it's because of the graph that I showed earlier, where I showed that iron is at the peak of stability. So the universe prefers to form iron, and that's why there's an iron peak in the current observed distribution of elements. So in order to get this, it's a process where the Big Bang formed mostly hydrogen and helium. This material collapsed to form galaxies. Galaxies produce stars. The stars live, the stars die, and then the elements get recycled back into the universe and become heavier with each step. How does this actually happen? In our sun, at the core, the hydrogen is getting fused together into helium, and that releases energy, and that's actually what powers the sun. Eventually, once it exhausts its supply of hydrogen, it will start fusing the helium into carbon and oxygen. So if it does this process in layers. But our sun will not actually advance to the next stage. Instead, what will happen is it will become a dead star. It will become a white dwarf at this stage, because it doesn't actually get hot enough or dense enough to fuse carbon and oxygen into the next level. You need a star that's about 8 times the size of the sun in order to reach the next tier of elements, silicon and iron. So for those stars, eventually they'll produce an iron core, and that iron core will get bigger and bigger and bigger until it can no longer support its own weight. And it will collapse, and that's called a core collapse supernova. So the core collapse supernova releases all of this stuff that's produced by the star into the universe. And this is the percentage of all of these elements that are produced in core collapse supernovae. So for instance, most of the oxygen is from core collapse supernovae, some of the carbon is. That's how you interpret this graph. But you'll see from the graph that it's mostly these intermediate mass elements that are produced by core collapse supernovae, and not much of the elements around iron. And that's because when the core collapse supernova explodes, most of the stuff in the core collapses into a neutron star. And there it stays forever, or until it collides with another neutron star, in which case you don't really get iron anymore, you get these kind of elements. So you don't really get the iron back when you have these massive stars exploding. Where the iron comes from instead is from white dwarfs exploding in thermonuclear supernovae. So when white dwarfs explode, instead of a core collapse happening, what's happening is somehow the fusion process starts again in these dead stars. And when they explode, they actually produce a ton of iron. So they're the source of most of the iron in the universe. So this is happening as generations of stars live and die. And you can actually see this whenever you look at a galaxy. So when you look at a galaxy, the first thing you'll notice are its spiral arms. One thing interesting that I'll tell you is that these spiral arms are not actually physical arms. What they are instead are what's called density waves. Think about like circular orbits just sitting still. It would just look like a featureless circle with no arms. But if I were to distort those circles, like just flick them so that they kind of wobble back and forth, what they'll form instead are ellipses. And since the inner ellipses move faster than the outer ellipses, you get the formation of these kind of arms. So what the arms that you see in galaxies are actually like a density wave forming from the galaxy wobbling. So it's just the galaxy formed, and then it's kind of jittering, and then these density waves look like arms. And in the arms, the bright points are higher density areas, and the dark points are lower density areas. And what you're actually seeing is stars are born when the arm passes through, because that's where the highest density is. Whenever an arm sweeps by, a generation of stars is born. When the arm passes, a generation of stars has died. So every revolution of a galaxy produces a generation of stars that lives and dies. You can see a simulation of this happening. Every revolution is a generation of stars. And this process actually takes 200 million years. It's a substantial amount of time, even compared to the age of the universe. Because the universe is only 13.8 billion years old. The galaxy formed pretty early in the universe's life at only 12 billion years. So only some 60-odd revolutions have actually occurred. We've only gone through 60 generations of stars living and dying. So I think that's quite fascinating. And one thing is, when people tell me that the universe has been around for a long time, what if there are super advanced civilizations that have been around for billions of years? One thing that I might add to that is that, well, if this process of stars living and dying is what creates the heavy elements that are necessary for life and the metals that are necessary for technology, then we are actually quite early in the galaxy's life. We're only 60 rotations in, and only 2% of the universe's material has been converted into heavier elements. So we don't actually have that much to work with, especially if we go back to earlier times. So how long will it take to burn everything up and not just have 2%, but have all heavy elements? Well, if it took 60 revolutions to burn up 2%, then if we just sort of naively extrapolate that, then it will take some 3,000 revolutions, or about 1 trillion years, to burn up all of the material in the universe into heavier elements than hydrogen and helium. But in reality, the process actually becomes less and less efficient, because as you run out of material to form stars out of, you can form less and less massive stars. And less massive stars can live for trillions of years. So 1 trillion years in the future, we might in fact have a lot of heavier elements, the elements that are heavier than hydrogen and helium, and then the stars that remain will be these really low mass red dwarf stars. So this is the universe. It's about 1 trillion years from now, a sea of red stars. And that brings me to the second part of my talk, which is measuring the universe. So I talked about supernovae and how they're the origin of elements. And I talked about two types of supernovae, the thermonuclear and the core collapse supernovae. In terms of observations, people typically classify them in terms of what we can see. And this is how we classify them. If you see a supernova explode and you break down its light, and you see a characteristic emission where you expect hydrogen to be. So you might have heard of spectra, like you break down light into a rainbow, like the sunlight, you can break it into a rainbow. If you break down the supernova's light and you see a hydrogen emission, then what we call that is a type 2 supernova. If you don't see hydrogen, but you see a silicon absorption, then we call that a type 1a. And if you see neither, then you call that a type 1b or c. We now know that these two classifications of supernovae are what core collapse supernovae are, whereas type 1a are the thermonuclear supernovae. So thermonuclear supernovae and type 1a are actually the same thing. Now the type 1a supernovae in particular have a very useful property in addition to just creating all the iron. They are what's called standard candles. Now this is a messy plot, but I only want you to focus on this part of it. So you see that gray strip that's labeled 1A? So this is a plot of brightness versus how long the supernova takes. And the 1A sit on this neat little strip, which basically means that they have a very uniform brightness, especially if you know how long they take. Like, suppose you knew that a supernova takes 50 days versus 100 days. You can then work out exactly how much you need to correct them by in order to know their exact luminosity. So whenever you see a Type Ia supernova explode, you can always know exactly what brightness it is. And that's what we call a standard candle. It's like if you're looking out into space and you're seeing a sea of candles that have the same brightness, then just by looking at how bright the candle is, you can tell exactly how far away that candle is. And we can use that as rulers to measure the size of the universe. So people did precisely that in order to figure out how fast the universe is expanding, which I talked about in the early part of the talk. People did this because they expected to see that the universe is either expanding uniformly forever, or it's going to collapse in on itself one day because of all the mass that's inside of it, right? So what would you expect to see in those two cases? If you had a uniformly expanding sphere and you take 2 points that are separated by a centimeter, then if you take another set of points that's double the distance away, then if this one expands by double, the other one also expands by double. So 1 centimeter becomes 2 centimeters, 2 centimeters becomes 4 centimeters, which means that as you look farther and farther away, the velocity increases. Like this one is moving away twice as fast as this one is. This one moved by 1, that guy moved by 2. Farther away means faster. So we expect to see this black line if the universe is expanding uniformly. Now, if the universe was decelerating, then what that essentially means is that there's an acceleration component. So you learn from like grade 11 physics or something that there's like if you have an acceleration, then you just take vt minus at squared. Acceleration is t squared. And for the same distance then, because it's reduced by at squared, the velocity then has to increase, which means that the graph moves this way. So for the same distance of object that you observe, its velocity should be increased if the universe were decelerating. But what we see instead is these red data points measured by supernovae, which show an ever so slight deviation upward rather than downward, which indicates that the universe is actually accelerating and not decelerating. And in order to make the universe accelerate, like if gravity can make the universe decelerate, then you have to have a source of energy that makes the universe accelerate. And if you calculate how much energy this is, it turns out that 72% of all the mass/energy in the universe has to be this dark, invisible energy that's accelerating the universe farther and farther away at an accelerated rate. And only some 28% is all the matter in the universe. This is a term that this kind of energy is something that Einstein actually predicted, because when he wrote his theory of gravity, he thought there's no way the universe is collapsing. The universe is going to be around forever, and it has been around forever, so it must be uniformly expanding. So he added a bit of energy to stop the universe from collapsing in on itself. What he did not expect, though, was that the universe is actually accelerating away. So there's actually a lot more dark energy than what his equations would suggest. And this discovery led to these folks winning the Nobel Prize in 2011. So knowing this, we can then tell the entire history of the universe in 3 epochs. The first epoch is the Epoch of Light, which relates to the first part of my talk, where I talked about the origin of the elements. And the Epoch of Light is essentially this phase, when the universe was an opaque furnace of light. And this is when the elements formed. The issue is when the universe expands, the density of matter drops, right? So because if you just have mass and you expand it, then it drops by the size cubed. The same thing happens to light, but even faster, because light does one more thing than reduce in density. Matter reduces in density, but light does one more thing. Light increases in wavelength. So if you expand a ball with like a wave on it, the wave will actually increase in wavelength, which drops the energy of the light. So the light energy density actually drops by power of 4 rather than power of 3. It's dropping faster than matter is. So eventually, the universe switches over from radiation-dominated, radiation meaning light, into matter-dominated, So at the point when the universe became transparent, it was 85% matter and 15% radiation. So the takeaway from this is that this epoch created the elements. The second part of the universe's history is the Epoch of Matter. And in this phase, what we were talking about is mostly dark matter, because we might have heard before that there's like 10 times more dark matter than there is, 6 times more dark matter than there is matter. I'm including both dark matter and matter. And in this epoch, it's when the cosmic web is formed. So the cosmic web is what people refer to when people show images that look like this. So this is is the animation here? When people show maps of the universe that look like these neurons, people are talking about the cosmic web. It's essentially, in the beginning, there's like these tiny perturbations, and then these perturbations collapse under gravity to form these strings, and these strings are where all the galaxies are. So the cosmic web is the formation of galaxies. So this epoch is essentially when all the galaxies formed. But now, from supernovae, we understand that we're in the epoch of dark energy. So at some point, dark energy as a component actually overtook dark matter. And we are living in that epoch right now. We're living in an epoch where dark energy dominates dark matter. So what implications does this have for the future of our universe? If you try to mathematically calculate how these cosmic strings will grow over time, you'll find that they kind of linearly grow during the epoch of matter under gravity. But as soon as dark energy overtakes matter, the rate at which the universe is expanding exactly cancels out the rate at which gravity creates cosmic strings, these cosmic web. And what you end up with is that the cosmic web will no longer form. So the structures that we see in the universe, these filaments, these neuron-like things, they're the last structures that have ever formed. And the universe that we see right now is these galaxy clusters that we are living in and that we are seeing. These are the last galaxy clusters that have ever formed and ever will form. So we're actually living in a universe that's frozen in time while our horizons redden and darken forever as the universe expands. So in a sense, you can say that our galaxy is really young and only some 60 generations of stars have lived and died. But in another sense, you can also say that we're living in the sunset of the universe that will last for 1 trillion years. And as the universe expands, eventually it's getting closer and closer to the speed of light. So we're not going to be able to see the farthest galaxies, and that horizon gets closer and closer to us until all we see is just red, dark, nothing. So as a recap, Type Ia Supernovae come from the explosions of white dwarfs, which are the most common end states of stars, like the sun. They produce most of the iron peak elements in the universe, and they tell us that the expansion of the universe is accelerating. But it leaves us with a question of, how do white dwarfs explode? Before I go to the third part of my talk, let me drink a water. You'll notice actually that this is a UFT AstroTours mug, which means that this can be you if you go to the UFT AstroTours merch shop. Okay, so how might you explode a white dwarf? White dwarfs are quite exotic objects, so I'm going to make a comparison to normal gases. So a normal gas, when you increase its temperature, the pressure inside increases, which causes the gas to expand. This is called the ideal gas law. But white dwarfs are not supported by the same kind of pressure that ideal gases are supported by. They're supported by something called electron degeneracy pressure. And if you've ever taken a chemistry class, then you know something called the Pauli exclusion principle, which says that electrons cannot occupy the same state. You can't put 2 electrons in the exact same state. They have to be in different states. Which means that you can't put 2 electrons in the same position and the same velocity. All the electrons have to be spaced out. And this actually exerts a pressure on the star that counteracts gravity. The pressure is given by this formula. It's related to the density of how tightly the electrons are packed. The more tightly you pack these electrons, the more pressure they exert, so they'll fight against gravity trying to push them together any further. But you'll notice that in this equation there's no temperature, unlike in the ideal gas law. In the ideal gas law, there's a temperature. If you increase the temperature, you increase the pressure. Here, if I increase the temperature, I can increase it however I want, but I won't change the electron degeneracy pressure, which means I can rack up the temperature to insane heights, and the white dwarf will just stay put. It will keep burning. And that's a very dangerous setup, because that means I can create an explosion. The way that the white dwarf actually explodes is another pressure has to begin taking over. Like the electron degeneracy pressure is going nowhere. Radiation pressure is not something that you normally talk about because it's usually so tiny. Like a light hits you and it exerts almost no force. But it increases by T to the 4th power, which means with temperature, as temperature gets really, really high, this radiation pressure actually becomes substantial, and eventually the white dwarf is ripped apart by light. So the white dwarf will eventually explode, but not before burning out all its elements. That's how it's so efficiently able to produce iron. So what is the energy source? It is the very production of iron that I was talking about. You take the carbon-oxygen white dwarf, and it's performing nuclear fusion. And this nuclear fusion process produces 10 to the 44 joules of energy. If you look at how fast a supernova is expanding, it's expanding at 10,000 kilometers per second. It turns out that all of this nuclear fusion energy is going into the kinetic energy of the ejecta. So the stuff that the supernova is ejecting out, the speed of it, the velocity, all the energy is going into that. What actually produces the light is the decay of this intermediate product, nickel, into the final product, iron, which takes on order days to months. And you see a supernova that increases in brightness over the course of 2 weeks as it becomes from opaque to transparent. And then you see a decay corresponding to the decay rate of nickel and then the decay rate of cobalt. So the supernova that you see is from this process, and the amount of energy that's released is actually only about 1% of the entire energy of the supernova. So a supernova, as very bright, it can outshine the galaxy that it comes from, but the light that you see is actually only 1% of the supernova's energy. Most of it comes in the form of ejecting the gas at a massive velocity that ends up getting recirculated back into the galaxy and forming new stars. Now, the third question is, how might you ignite this fuel? How do you start the fusion process in a star that has already died? So to understand this, you have to understand another bizarre aspect of white dwarfs, which is that they're very small. Like a white dwarf star is not how you expect a normal star to look. A white dwarf star is only about the size of the Earth, but it has the mass of the Earth. So it's extremely dense because of the fact that it stopped burning. Like the hydrogen fusion process, or the fusion process in the star's core has stopped long ago and has already collapsed into this degenerate object. And a crazy thing is that as you increase the mass of this object, so you increase the white dwarf's mass, you actually decrease the white dwarf's radius. So you make the white dwarf more massive, it gets smaller and smaller and smaller, until you hit something called the Chandrasekhar mass. So this Chandrasekhar discovered that if you increase the white dwarf to about 1.4 solar masses, its size goes to 0. So when that happens, you essentially are creating the conditions for like basically the Big Bang. You're becoming a singularity. And then somewhere in the middle of that process, you're going to start a nuclear fusion, and then the white dwarf explodes, as we discussed earlier. So the problem, and that affects eventually how the distribution of elements in the supernova will look, because when you go subsonically, you can have mixing of gases and metals and all that. So there's kind of like a zoo of possibilities of how to ignite a white dwarf. And that kind of leads me to talk about the zoo of observations that people are finding from Type Ia supernovae. So Type Ia supernovae, as I said before, are like these kind of very uniform objects, or so people have thought. But the more Type Ia supernovae we find, the more we discover that they're not actually as uniform as we thought they were. There's actually quite a lot of diversity, many different subtypes of them, in fact. There's a distribution. Most of them tend to be normal, and some of them tend to be more bright than average, and some are less bright. And there are some that are even extremely strange, like ones whose inferred mass is actually higher than the theoretical mass limit. which is a kind of open puzzle that we're still not sure what the solution to is. But those are extremely rare. And there's also some peculiar events that are extraordinarily dim. And they can account for actually quite a lot of supernovae, because in this kind of dim region, because they're dim, they're harder to observe. So it's possible that they actually account for much more supernovae than we thought. So considering that there's so many types of type 1a supernovae, and they're all slightly different, it kind of begs the question of how standard exactly are these candles, right? Like you can see from this graph already that there's quite a lot of scatter at the end there in terms of data points. They don't really lie on a straight line. You know, how standard are they? And it's like looking at birds and trying to figure out how far away continents are. Like you look at continents and you look at the birds flying over them and you're trying to figure out how far away the continents are, you know? Could it be that different environments just produce different sizes of birds, you know? There could be systematic effects like this that can affect how bright a type 1a supernova is. But if we were to understand the process that creates birds, like understand them mechanically, so that a bird to us is almost like a machine. We can understand exactly what kind of bird will form from exactly what kind of environment we observe. If that is the case, then the bird suddenly becomes an extremely precise instrument for measuring how far away continents are. And if that were the case, we can do things like, we can try to squeeze down this distribution to see, is there really this much dark energy? Maybe there's more dark energy than we thought. Maybe supernovae back then are just brighter. Maybe there's less dark energy than we thought. Maybe dark energy is not constant. It's possible that there could be variations in dark energy. Can we figure out how dark energy has evolved over the universe's history? And if we can figure that out, maybe we can understand what dark energy is. Which leads me to the next part, where we try to understand exactly this problem. We try to figure out how exactly a type 1a supernova explodes. And the way we have chosen to do this is we chose to look at the earliest few hours to days after the supernova's explosion, because many clues to the supernova's origin are hidden there. For instance, if you have like a star, like a giant companion or like a normal star beside it, then as the supernova is exploding, it should run into that star, and that produces some extra emission that you would be able to see. If you had like another white dwarf present, then you can collide into that white dwarf and produce dimmer emissions. So depending on what's in the supernova's progenitor system, you can have different observable effects in the first few hours to days. And then trying to find the colors of these supernovae in the earliest hours to days is also important, because the color can tell you about the spectrum. Like if you take a beam of light and you break it down into its rainbow components, depending on what components there are, it can look red or blue. And people have found recently especially that, if you say have this hydrogen bomb process that starts from the outside and explodes inwards, then you should have a bunch of iron on the outside, and that's spectroscopic features that redden the star's light. So if it looks red, you can tell that there's iron there. So we looked for this using the KMT net, which is the Korean microlensing telescope network. There's 3 telescopes in the southern hemisphere, in Australia, Africa, and South America. And what we use these 3 telescopes to do is, because they're distributed in this kind of triangular formation, we can look at a patch of sky continuously over a 24-hour period. So as the sun sets for one telescope, the sun rises for the next telescope, right? So it's always going to be night somewhere. So we can keep our eye on a patch of sky and look for supernovae from it. Each telescope is equipped with a camera that gives you about this much field. So we're looking at a patch of sky that's about this big, and we focus them on nearby galaxies to find supernova from them. And the telescope network is equipped with filters that are analogous to the human eye. So the human eye has rod cells and cone cells, and we have 3 different types of cone cells that can tell you the colors. Like we can detect red light, green light, and blue light. Similarly, our telescope can detect blue, green, and red. Other telescopes have different kinds of filters, and that's because different filter systems are sensitive to different effects. Our filter system in particular is sensitive to the presence of iron, which is produced in supernovae. So given that, using this very unique setup, we were able to find some of the earliest Type Ia supernovae ever detected. And I can show you full color RGB videos of them. So here's a supernova exploding in this elliptical galaxy. You can see it going off in the center. And then here's a video of another supernova going off in this dramatic spiral galaxy. Now, in particular, the first video that you see on the left-hand side is actually the earliest Type Ia that has ever been detected. So as soon as the supernova exploded, we already got observations on it, and no one has ever gotten earlier observations than we have. And we got observations about 1 hour since the first light emerged from the supernova. And what we saw is a light curve that looks like this, shown by the colored data points. And the black data points are what has been seen in other supernovae. So from this plot, you can already see that we're in a kind of earlier and fainter regime than what has been seen previously by about 1 day. And in this regime, I'm going to point out some very surprising features. So first, you can see that the red and green data points are kind of going up, so they're rising. But the blue data points are just sort of stagnated. And this leads to a color that evolves like this. Because there's a lack of blue, what it causes the color to do is evolve red, because the blue is gone. So the supernova becomes extremely red. And at the peak of the reddening, it's actually redder than what has ever been seen in the Type Ia supernova at these early phases. So it's extremely red. And following these early observations, we got a lot of follow-up. So from ground-based and space-based telescopes, we got observations in all parts of its spectrum, from the ultraviolet to the infrared. And then we got observations hundreds of days after the supernova's peak in order to really constrain what the origin of the supernova is. So let me start by telling you what we make of this reddening. So to investigate what the origin of the reddening is, we looked at how the spectrum or the components of the light are distributed at the reddest phase. You can see the blue, green, and red component at that phase. And this is a very strange distribution for a Type Ia supernova, because in these early stages, the supernova is like a very dense ball, which means that all the light should be kind of randomly distributed, and kind of like it should be distributed according to the temperature of the gas, kind of like the random motions of a gas. But that's not quite what we're seeing. Like if we see something that's just temperature distributed, it should look like kind of a smooth, flat profile, but we're seeing something that's quite distinctly discontinuous. In fact, if you look at any two of those components, it requires a temperature that just doesn't really make sense if you ever include the blue part. Like, if you want the blue part to be this low, you need a temperature that's like only 5,000 or 3,000 Kelvin, which is even colder than the sun. And how can the supernova be colder than, just the sun? So it cannot possibly be this cold. There must be something in the supernova spectrum that is suppressing the blue part of its light. And naturally, what we suspected is iron peak elements because of this complex of iron lines that falls between the B and V bands. So we simulated what would happen if we placed iron in the very outer reaches of the supernova. So this is the supernova's core. It produces a ton of iron because, as we know, Type Ia supernovae produces iron. If we just add this clump of iron peak elements to the very outside, what you end up getting is a spectrum that looks like this, with a clean break between the B and V bands. And this ends up reproducing what we observe. So it seems like the surface iron peak elements is the origin of the reddening that we see. So in terms of the supernova's origin, where can the surface iron peak elements come from? And there's two possibilities. One is this hydrogen bond process, where if you have this two-stage ignition, then the first stage of the ignition produces the outside iron peak elements, and the second stage produces what's on the inside, and that can clearly explain the observations. And that leads to a supersonic explosion. The second possibility is if you have a Chandrasekhar mass explosion that's just like at the critical mass and explodes from the center, it's still possible to get iron out there if the explosion were slow enough and asymmetric enough. So you need the explosion to go off center, and you need it to be slow so that it mixes. I'm going to point out two things. One is that this actually makes sense with what we observed later in the supernova, because as we see several hundred days following the supernova when the ejecta has thinned out, we see really blue shifted lines, which indicates the supernova might actually be asymmetric. So the asymmetry actually does pan out. But this doesn't rule out the other possibility, because when we simulate what happens in this two-stage hydrogen bond process, this actually also turns out to be consistent with asymmetry. Like if you have a convergent wave from the shell detonation, it rarely converges in the exact center. So both possibilities are actually consistent with off-center ignition. In terms of the progenitor system of the supernova, we got constraints from the early phase as well as extremely late time. So just comparing what we see in the early time compared to what we would expect from collision with a star, we're able to rule out all the stars that are more massive than, like, say, the sun. If you go heavier than the sun, most of the parameter space of allowed collisions are ruled out. So in other words, the only objects we could have collided with are extremely small stars or other white dwarfs. And this is also favored by what we see in very late times, because if you have other star present, then the supernova will sweep up the other star's stuff, including hydrogen if it's a really big star. And we see almost no hydrogen. So this disfavors the presence of hydrogen-rich companions like stars and giants. So from this, we seem to favor this possibility. So these observations essentially tell us that Type Ia supernovae probably emerged from one of two channels. So we've basically taken this zoo of possibilities and narrowed down there's two possibilities. And more observations are required to confirm the two, possibly from the same phase that we observed them, but we just need more samples. Like right now, we just have two supernovae observed that's this early. But if we had more, then we can tell, say, like if it's the two-stage hydrogen bond process, then it's kind of symmetric, right? So from every direction, you should see that there's iron. So if that's what we see in every supernova, this seems to be the way to go. But if we only see it in 2% of cases, then that seems to be the way to go. So we're close to the solution, but we just need more samples. And that concludes my talk. These are references for various information that I provided, and the first paper there is actually the origin of the cover slide. So this is a paper that we published on the earliest Type Ia supernova, which made the cover of Nature Astronomy earlier this year. Yeah.
Great, is this working? Maybe a little. Great, thank you so much, Chris, for that amazing talk. If you could come back up here, we can take some questions.
Oh, yeah.
And just please remember just to repeat the question so then everybody can hear it. Yep, you can choose whether you'd like.
I didn't know who put their hand up first, so I'll start front. Blue.
So is it possible to create a small, extremely dense Chandrasekhar exceeding white dwarf star? And if so, how much interstellar gas do you need to make it?
So the question seems to be, can you create an extremely small white dwarf that's very, very close to the Chandrasekhar limit? That's very interesting, because you expect at the Chandrasekhar limit, it'd become a singularity, right? But the thing is that, as I was talking about before with the ignition of the white dwarf, it never quite gets there. Like, it will get to a point where it's so dense that the carbon will ignite, and that's it. Because these stars are filled with carbon. Uh-huh. Oh yeah, if you wanted to sort of manufacture one. Yeah. Okay, so the question is, if you wanted to manufacture a white dwarf that's close to the Chandrasekhar limit, that's quite possible. In fact, actually, that's exactly what happens. That's exactly what people think happens for Type Ia supernovae. So if you have a white dwarf that's sitting there, it is actually funneling in gas from its companion. It has a companion star there. the gravity of the white dwarf eventually sucks in mass from the white dwarf, so it's similar to the process that you're describing. So the white dwarf is slowly growing in mass, and it's coming nearer and nearer to the Chandrasekhar limit and getting smaller and smaller. But it won't get infinitely small because at some point it's made of carbon and oxygen and it'll just ignite. If it were made of iron, though, you'd get a black hole.
Also, if you want to write a paper about it, you don't have to credit me.
Black shirt.
I've heard a pretty silly question. Do white dwarf stars give off light and then planets just like fall around?
Do white dwarf stars give off which light? Heat and light. Yes, it does. Yeah. So a white dwarf would just be a really blue. If you orbited a white dwarf, you would just have like a really blue sun. That is possible. People have talked about planets around white dwarfs, but we have not found one yet. The closest thing we found is a brown dwarf around a white dwarf, which is a failed star, but nothing small enough to be considered a planet. But we're getting there. We're getting there. I think blue shirt. Sorry? Can we detect the galaxy clusters from beyond the horizon? Sorry, I can't quite hear very clearly.
Can we detect those galaxy clusters that are moving over the horizon?
Oh, that are moving over the horizon. Yeah. So that's a very interesting question because as you're looking out into space, you're also looking backwards in time, which is why eventually you'll get to a point where you're going so far back in time that it's before the birth of the universe. So what we are seeing is eventually the galaxies are getting younger at the edge until eventually they're like 0 years old, and all you see is the photon furnace, or at least the echo of it, which is now only 3 degrees Kelvin. So as they're going over the horizon, probably what you'll see is they'll just become part of the cosmic microwave background. Yeah. I think Red Shirt had a question that was there for a while. How does the presence of iron? So iron has absorption lines. So every element actually has, every atom has absorption lines because there's like layers to the atom, and electrons can only occupy certain states. So it can only absorb certain photons, like a specific wavelength of light gets absorbed by this atom. Any other wavelength gets excluded. So the fact that we are seeing like this sharp transition at a place exactly where we would expect iron to have these transitions is indicative of the fact that there's iron present. I think gray sweater. Yeah. Sorry, at the beginning?
At the beginning, you said that the universe
Galaxy wobbles. Yeah. Uh-huh.
So what causes it to wobble?
So it could be left over from when the galaxy formed, because as the galaxy is forming, it's a quite dynamic process, right? You can expect a lot of motion there, and you can expect several bounces before it kind of settles into its shape. Or you can have galaxies that interact with neighbors. Because in these kind of cosmic web filaments, there's a lot of galaxies that are rather close together, and they're all like gravitationally interacting. Like our galaxy is interacting with the neighbor galaxy Andromeda, and eventually we're going to collide. And you can imagine that sets up, wobbling. So there's a lot of interaction.
There's, in the formula, you said the explosion in the Type Ia Supernova, they happen because of each of the 4 elements that are excited to increase in pressure. So what causes the increase in temperature?
So the cause of the increase in temperature is from the nuclear fusion process. So as you get to that certain critical density, the elements start fusing, and as they're fusing, they're getting to a more stable state. So if you imagine breaking up an element as paying the price, you're paying the price to break up an element. Well, the nuclear fusion process is doing the opposite. As you fuse the heavier and heavier elements, it's actually giving us energy. So nuclear fusion produces energy, and that's actually what powers the sun. So this fusion process is the source of the heating in the white dwarf.
And also one last question. How do you simulate all of this? Well, you can't really simulate every single point in the universe. And how much accuracy do you know that you have?
Okay, so if you wanted to simulate, say, okay, well, it depends on what you're trying to simulate. But typically, for a specific process, you need enough particles to accurately represent how that process is going to evolve in nature. For instance, if you have like a galaxy, if you want to simulate like how a galaxy evolves, you need to you cannot possibly simulate every star because that's way too many stars. There's 100 billion stars in the Milky Way, you know?
How many stars do you simulate? How much matter do you simulate to actually get accurate results without using?
Eventually, this is actually a rather detailed question. So you have to essentially combine stars. Like every point in that galaxy that I showed actually represents a certain neighborhood of stars that's on a scale that's irrelevant to the evolution of the galaxy. So there's a kind of equation that you can write out that basically tells you at what point would this cluster of stars be considered, independent stars versus it's just part of the overall galaxy. And we determine that point precisely for every simulation that we run so that we choose, this set of stars is considered one star. Yeah.
And when we're in the later stage of the universe, we do the same method for combining different sets of particles again.
For different phenomena, you would have different choices to make. Yeah.
Thank you.
Okay, I think we can take one final question before we wrap up and move on to the demos part. You can choose one last question.
I think green beanie.
So I heard that for supernovae, larger using those, the case of Type 1A, how much of the energy is released compared to the light and the speed of the ejecta?
So for Type 2 supernovae, how I understand is that when Type 2 supernovae explode, they're actually opaque to neutrinos. So a lot of the ejection of the Type 2 supernova's material comes from the neutrinos getting absorbed. Now we typically don't think of neutrinos as being absorbed by things. Neutrinos tend to pass through all the matter that it encounters. But in Type 2 supernovae, because like the interior layers of the ejecta are so dense, it actually traps the neutrinos and they don't get released, they just turn into kinetic energy of the ejecta. So Type 1A supernovae have like a kind of, it's different. So the heating doesn't really come from neutrinos so much as from the nuclear fusion process that creates just fast moving elements and gamma ray photons. Yeah.
Great, thank you so much, Chris. This was extremely interesting. And then just before we head off, I'm going to give a little bit of instructions of how to get to the post-talk activities. But first, I'd like to say thank you to our volunteers. Without them, the event wouldn't be able to happen. And also to our sponsors. They're also very important for the event to happen. Great. Okay. So now we're going to be heading over to the Astro Building and the McLennan Physical Laboratories. If you have a lab tour ticket, which we're handing out at the door, there'll be 3 different times. So if you have one that says 9:10, please meet Harlan. You can please raise your hand. Oh, sorry, the volunteer Harlan. Okay, I don't know who they are, so we'll get back to who they are in a second to show you.